All right, so the last speaker of the morning session is Professor Kenji FUKAYA from Simon Center of Geometry and Physics. So he's talking about Floer homologies, Lagrangian correspondence, and Atiyah Floer conjecture.
Thank you very much. Thank you for invitations. Happy birthday, Gam, for 60-year birthday. And actually, I myself is 65, so we are same age. And in Japan, most of the national university retirement age is 65. And since I am moving to China from Stony Brook, recently I need to sign several documents. And in those documents, I have to say that I retire from Stony Brook University. And I'm not so very happy to sign such a document because I don't have any intention to retire. I want to keep working. And fortunately, probably Gantian do not need to sign because he's in Beijing. I hope we together keep working next 5 years and meet again in some 70-year birthday conference.
Welcome.
Okay, so now I want to try to do these three things. So I'm sorry, only first page is other pages is in my dirty handwriting. So I want to talk three topics. One is this Atiyah Floer type conjectures. I will explain it. And the second thing is related to some symplectic quotient and how this Lagrangian Floer theory behaves for a symplectic quotient. And the third thing is called Lagrangian correspondence. And I want to explain many things. And actually, so the organizer mentioned that this is something like a kind of talk, and which I don't want to talk so much detail of the works, and even not so much precise statement, but just want to what kind of ideas are there and which kind of works have been done. So, okay, so now I want to explain what is Atiyah Floer type conjectures. So suppose you have just three manifolds, y1, y2 with boundary, which is sigma. And you have a vector bundle, typically SO3 or SU2 bundles. And you assume that the restriction of this bundle on boundary is isomorphic. Then you can group Y to two manifolds to get closed three manifold Y and a vector bundle E on it. So this is a situation of Atiyah Floer conjecture. Oops. So now, we consider this. So this is the picture. You have this y1 whose boundary is sigma and y2 whose boundary is sigma. You get y, which is a closed manifold with bundles. And there is one type of Floer homology that is called instanton Floer homology. And to define it, we use a flat bundle, flat connections on E, and also use a gauge theory on y cross R to define boundary operator. So this is the gauge theory Floer homology. And the other thing is the following. So we consider R of sigma, which is a modular space of flat connections on a Riemann surface. And this is known to be a symplectic manifold. And here, this yi, it is three manifold. And if you take the space of flat connections, typically or after perturbations, this guy became a Lagrangian submanifold. And the Atiyah Floer conjecture, so you have this Lagrangian Floer homology, and this is gauge theory Floer homology. And the Atiyah Floer conjecture predicts that they are isomorphic. And as I said, that I don't want to make it so much precise because it is rather hard. Sometimes it is very hard to make sense of this isomorphism. I mean, even define both sides. But this is in general the Atiyah Floer conjecture are supposed to be. So now I want to go to the next thing. It's a Lagrangian Floer theory of symplectic quotient. That's the following problem. Suppose X is a symplectic manifold, say compact, and suppose you have an action of compact Lie group which preserves symplectic structure. And suppose you have a map from X to the dual of the Lie algebra of G, which is called a moment map. It's just related to this Hamiltonian vector field. And then you have this symplectic quotient that is just mu inverse 0 divided by G. And let me assume that this quotient, so this is symplectic, and we assume that this quotient is smooth. It means that the group G is, has no fixed point on this level set. Then the conjecture is that you have a equivariant Lagrangian Floer theory on X, then it is something related to this Lagrangian Floer homology on the symplectic quotient. And more precisely, so we consider this Li, which is a G equivariant Lagrangian submanifold of X, assume it happens to be contained in a zero set of the moment maps. Then you take then this quotient L1 over Z and L2 over Z. This is a Lagrangian submanifold of symplectic quotient, and it is expected that this Floer homology of this Lagrangian submanifold is isomorphic to the G equivariant Floer homology of L1 and L2. There are several versions which is proved. I will go back to that. And this is something like some kind of a problem how this Lagrangian Floer theory is related to symplectic quotient process. And then the third thing I want to explain is Lagrangian correspondence. So Lagrangian correspondence is something like this. So you have two symplectic manifolds, x1 and x2. And if you have a Lagrangian submanifold L1, L2, which is a direct product of x1 cross x2, and the symplectic form is just a minus sign on a first factor. So such a Lagrangian submanifold is said to be Lagrangian correspondence. And it is Weinstein who proposed that morphism of the category of symplectic manifold should be Lagrangian correspondence. And the general conjecture and some statement is that if you have this Lagrangian correspondence, you have a functor from infinity category associated to x1 to the infinity category associated to x2. So these three are kind of topics I want to explain today. So I just three situations, and I explained that how these three are related to each other. So the first is Atiyah Floer conjecture, and the second is symplectic quotient. And actually, this Atiyah Floer conjecture may be regarded as a kind of infinite dimensional version of this symplectic quotient things. So in which sense? So let X be an infinite dimensional symplectic manifold of all connections on sigma 2, and you take G, a group of gauge transformations on this boundary on a Riemann surface, and this action with gauge transformation is known to be a moment map, known to be Hamiltonian and symplectic actions, and its moment map is known to be the curvature. So it means that the symplectic quotient is this space of flat connections. So this is X, and then this symplectic quotient is this space of flat connections. Then you say that symplectic side, this Lagrangian Floer theory is here, and the gauge theory side, you have a kind of you have something like equivariant Floer theory on this space of all connections. That is similar. That's a kind of similar to this instanton Floer homology. So this isomorphism between instanton Floer homology and the Lagrangian Floer theory is regarded as a infinite dimensional analog of the second point. So the relation between the second and third point. So second is a relation between symplectic quotient and the Lagrangian Floer theory, and the third is related to Lagrangian correspondence. And this relation is very much explicit. So suppose you have an action of G on symplectic manifold, and mu is a moment map. Then you consider this particular set, X pair of xy in X cross this symplectic quotient, so that X moment map of X is 0, and Y is an equivariant class of X. Let me recall this symplectic quotient is mu inverse 0 divided by G. So you have this particular subset of minus X cross X divided by G, and one can easily show that this is a Lagrangian submanifold. So you have some Lagrangian correspondence from X to X minus G, X divided by G, and in the third point should be from this Lagrangian correspondence gives some infinity functor from infinity category associated to X to infinity category associated to X divided by G. So this Lagrangian correspondence should be related to this second problems. So that is the relation between 2 and 3. And maybe I can say more about 1 and 3, but actually it's kind of many of the approach to study these two problems are very much similar, and you have very parallel things between these two problems. So in a sense, it is very, and there is actually more direct relations. It means that you have a 3 manifold whose boundary is sigma 1 and sigma 2. Then this 3 manifold gives a Lagrangian correspondence between space of flat connections on sigma 1 and the space of flat connections on sigma 2. So it is this direction is more more direct. So these three problems are somehow interrelated, and you can do a very parallel approach to these three problems. And actually what I have been working on this 5 years or something is somehow related to these three problems. So, so I said that I never make explicit statement or conjectures or definitions. And to make it explicit, we need to be more careful. So first of all, we need to include immersed Lagrangian submanifold to have enough wide range of Lagrangian submanifold. And also, let me see. So the reason is that, so for example, in the case of gauge theory, so you have a three-manifold whose boundary is sigma. Then, as I say that the space of flat connection Y is typically a Lagrangian submanifold of space of flat connection on sigma. But in general, this is even after generic perturbations, this is immersed Lagrangian submanifold. And if you restrict to embedded case, you lose something. So that's one important point. And the second is that we need to use something called a bounding cochain. I don't want to define it, but you have a Lagrangian submanifold and you have infinity algebras. And the bounding cochain in infinity algebra is a solution of these equations, which is something like an infinity analog of Molar-Cartan equations. And this bounding cochain is used to kind of define Floer homology. So now why we need this bounding cochain? So if you have this three-manifold Y1, three-manifold Y2, whose boundary is sigma, then actually some version of Atiyah Floer conjecture we can make a bit more precise. Right-hand side is something like this. It contains not only Lagrangian submanifold Ry1 and Ry2, but some bounding cochain of Y1, associated Y1 and Y2. And this bounding cochain is some extra information which actually came from gauge theory. So this is the kind of thing I need to do. But I don't want to explain so much. So this is some and since these three works are related to so many works of many people, I try to write some names. And I'm sorry to say, probably the list is not complete. It is almost impossible to write down the complete list. But I wrote some names. So this Atiyah Floer conjecture, of course, Atiyah Floer. In 1990s, there are various people working on it. Dr. Salmon, Yoshida Lee. And I wrote something. And in 2000, maybe very famous, and Salomon do some serious works. And at the end of 2000, Lipinski came to have some other works. And recently, there are many people. And I'm sorry to say that I cannot list all people, but there are, and I did some work with Alkabet Naimi and Lipinski. I'm sorry I cannot list all the recent works. And so now, it's about this second point. And this is related to something called the gauge sigma model. And there are many people involved in this gauge sigma model. Mundet, Rivera, Chilibak, Salomon, Woodworth, Tiam, Gagu, Boxiu. Probably there are much more, but I don't know enough because I don't work with it myself. And there are work called Telemann's conjecture. And I wrote something, and there are several recent works which is related to this using correspondence for these problems. I'm pretty sure there are many others. And for the third thing about the Lagrangian correspondence, and where Herman Woodworth started it, and there are students more also involved. And there's a work by Lekiri and Lipinski, and there's a work by Botman Wilhelm, and I am writing something. Probably there are something more, but I forgot it. Okay, so now this is there's a name. So now I want to explain some methods to study these problems. There are basically two different kinds of methods. One is a direct analytic approach. I will explain which kind of analysis one can use to study these problems. The other is something I want to call cobolism method. And actually, I mainly work on this cobolism method. It means that I try to avoid analysis as much as possible. Probably, as Mohammed said, this is not so natural for this conference on geometric analysis, because I am in a side to forget geometric analysis as much as possible. And there are many other people who use very interesting geometric analysis to study these problems. So I want to explain what is this. So what is direct analytic approach? So in the case of Atiyah Floer type conjectures, one can consider the following things. You have this two manifold B and four manifold X, and you have a fiber bundle whose fiber is this Riemann surface. And we consider gauge theory on this four manifold, which is kind of like ASC equations on this four manifold. And analytic approach is the following. So you consider this metric on X4, but then we consider the limit so that this metric on the Riemann surface shrinks, getting smaller and smaller, and finally go down to this base space B. Then kind of naive observation is that AC equations on this four manifold boil down to the pseudo-harmonic curve equation on B if you shrink these fibers. That kind of thing is known in the 90s, probably one of the reasons that Atiyah Floer made these conjectures. And this is not so easy to make rigorous because of this difficult adiabatic problems. This is a direct analytic approach to study Atiyah Floer type conjectures. And that is what basically the Salomon and Wilhelm did out of this kind of things, and the scholar Salomon did, and that kind of things. Okay, now the second is something that analytic approach is something called a gauge sigma model. And the gauge sigma model is a mixture of gauge theory and pseudo-harmonic curve. So I just want to explain something like this. So you have this two-dimensional manifold, and you have a target simplex manifold X, but you have a fiber bundle whose basis is sigma and whose fiber is X. And you consider, and the G is something, so you consider some harmonic sessions. And then again, you shrink this X to a point where you shrink sigma. So you have a two adiabatic limit, so that fiber is very big and the fiber is very small. And to kind of combine these two limits is something called an important part of this gauge sigma model. And this gauge sigma model can be used to study this relation between P and between kind of simplex geometry of X and the simplex geometry of simplex quotient. And that is done by many people, like Tiam and Gangubo. So now, the third thing is a Lagrangian correspondence. And for Lagrangian correspondence, there is some analytic approach called strict shrinking and finite bubble. That is mainly studied by Botman and Wilhelm. I want to say a few words about what it is. So now, there is something called the pseudo-harmonic kilt. Pseudo-harmonic kilt is something like this. You have a Riemann surface, which is divided into subdomains. And one consider this harmonic map in each subdomain UI, and UI goes to various simplex manifold, which depends. In a different domain, you have a harmonic curve to different simplex manifold, and on these lines, you put some matching conditions, and that is something basically called pseudo-harmonic kilt. I'm sorry, I cannot explain so much. It is a work by Wilhelm and Woodworth. And then how to use this kind of thing in analytic approach is the following things. So this is a kilt, and then you change the width of each strip. So this guy gets narrow, and finally it gets width is 0. So you have something like a family of the moduli spaces, which is parameterized by the width of one strip, and then those people consider the limit when this width goes to 0, and what happens in this singular limit. That is a problem called strip shrinking, strip shrinking the point. And then there is something called a finite bubble happens on this shrinking. And this strip shrinking, if you just look this analogy using this infinite dimensional simplex quotient, actually is somewhat much related to this gauge theory case, for that fiber shrinks the point. So they are kind of, both analyses are the most related. Maybe to relate it directly is not so easy, but kind of at least philosophically, these are related. So this is an analytic approach, and you can see that this kind of singular limit is not easy to study. And in another two approach, you have something like asymptotic behavior, and in gauge theory, you have some adiabatic limit of these nonlinear equations. So they are interesting and very challenging analytic problems. And to study these interesting analytic problems, one can get some information about these three problems. So that's analytic approach. So now what I want to say about the cobordism approach. So as I said, that cobordism approach is somehow to go around this kind of difficult analysis and kind of do some more homological algebra to avoid this analysis. And so now what kind of homological algebra we use is the following things. So suppose you have this two infinity category in all three situations, we need a kind of infinity category, and we want to construct some infinity functors. So we have two infinity categories, and what we want to find these infinity functors from one of the infinity category to the others. And it is sometimes difficult to construct directly the functors. Then we replace this infinity category C2 to something called a functor category. So I mean, you can imagine that if you have a usual category C, then you consider the all natural transport functor from op C to the category of set. Then it is another category, and C2 is included this functor category. That is the famous Yoneda lemma in category theory, and you have a similar Yoneda lemma in infinity category. So you have this canonical embed Yoneda functor, and in many cases it is easier to cook up this functor from the first infinity category to this functor category. For this we use some moduli spaces, but actually those moduli spaces is somewhat easier than a direct analytic approach. For example, in the case of Lagrangian correspondence, we need kilt. We need this. So we need this kind of moduli space, like several harmonic curve to different domain. But to construct this functor, we do not need this this strip shrinking. So this difficult adiabatic and this singular limit, you don't need to study. You only need this part, and only use this. So then for this slightly easier analysis, we get this infinity functor. So now it is some kind of a problem that this is somehow space of all kind of modular problem, and you want to prove that this guy is representable on this after C2. Maybe some analogy is the following: if you have some distributions on M1 and M2, and you have some smooth functions on M1, then you go up and go down. This is the Schwarz kernel. So you have some distributions on M2, and then in analysis you want to prove regularity on this map. And this regularity is somewhat related to the representability. So you prove this representability, then combine this, and then you get this functor you want. So this is something like a homological algebra trick to avoid some difficult adiabatic argument in analysis. So that's called cobordism argument. So in the case of Atiyah Floer conjectures, we need something called a mixed moduli space, which is introduced by Lipinski, and that is a mixture of ASD equations and the pseudo-harmonic curve equations. I don't want to explain it, but it's something like an infinite dimensional analog of the moduli space of pseudo-harmonic kilt. So if we can use this mixed moduli space, then we can cook up this infinity functor to this. So we can cook up this kind of infinity functors. We can cook up this kind of infinity functors for Atiyah Floer conjecture, and then the rest is just the representability of the image. So that's our approach to Atiyah Floer conjecture. Okay. So now, what is the present status of this? So first of all, this is Atiyah Floer conjecture. So we have written the papers. In a case, this three-dimensional Lagrangian is actually embedded, and this space of flat connection on sigma is smooth. In that case, we proved our result. And the case when this space of flat connection is smooth and this Lagrangian is immersed, I think I wrote some announcement many years ago, and we are still writing, but we believe we can write it up in the future. And these are the work by Lipinski and Daimon Lipinski and myself. And then and there is another approach which is related, but Gangu Bokshu wrote something parallel to this Botman's Wilhelm's work, and some part of this he wrote it, and maybe he go to this more analytic approach. So this is part one. Yeah. So part two is about this symplectic course. Part three. So part three is about this Lagrangian correspondence. So assuming every Lagrangian submanifold appearing is monotone, Wilhelm, Woodward, and Moe wrote it using this adiabatic approach, and Lekiri and Lipinski wrote some other papers on similar situations, but they replaced these analytic things with cobordism argument. And in a case that is more general, I wrote some papers in Ma's case several years ago, and there are work in progress by Botman and Wilhelm, and those work are more analytic approach. So that's the present status. And part two, I'm sorry, there are so many works and I cannot write the summary. So and I myself is not a specialist, so I'm very sorry. I just do not mention this. So now I want to do some future plan. what is not yet done, and I want to do it in the future. So first thing is something like making a Atiyah Floer conjecture more functorial. So what I mean by that? So I say that this is an isomorphism of these two Floer homologies. And this more functorial thing is that I want to cook up some homotopy equivalence of infinity category, so that this isomorphism is a kind of a morphism part of the story. And I want to explain what should be what should be this what should be gauge theory side of this category. So we fix this Riemann surface, and I want to cook up some infinity category associated to this Riemann surface. And then the object of this category is 3-manifold Y whose boundary is sigma. So that's the object. Then you have two such a 3-manifold. Then what is a morphism? Morphism is a kind of flat connection or instant Floer homology of Y1 and Y2 glued over sigma. So that's the natural morphism space. And I want to define what is the composition of the morphism. So you consider this 4-manifold. So you take this Y1 and Y2, and here is some sigma cross domain. And this is Y1 cross Y3, and this is Y2 cross, and this is the end. End is Y1 glued Y2 cross R, and Y1 cross Y3 cross R, and Y2 and Y3 cross R. So you have a 4-manifold which has 3 end at infinity, and then you take something like a Donaldson invariant with instanton homology as a coefficient, and that should be the composition of this morphism. And if you see if you look at this definition of infinity structures on Lagrange Floer theory, then you can just you have this kind of diagrams, and you have this kind of family of metrics on a 4-manifold, and it gives the infinity structure. So that is something like infinity category on the domains. And something I want to prove, and with diamond, is that using this infinity category in the gauge theory side, and usual infinity structure on the Lagrange Floer theory side, this Atiyah Floer conjecture became a functor. Infinity functor. I believe we can do it, but yeah. But of course, it is not written. So now, the next thing is the following things. I want to relate this Lagrangian correspondence and things with open closed map. That is another open part. So suppose you have the L12, which is a Lagrangian correspondence. It's a Lagrangian submanifold of x1 cross x2. Then, as I mentioned, that we can associate some functors from infinity category on x1 to infinity category x2. So you associate these infinity functors. And the problem, which is the conjecture, is the following. So you have this Lagrangian correspondence and infinity functors, and the Hochschild homology is contravariant with the infinity functor. So it induces this homomorphism of Hochschild homology. And you have this x1 and you have this x2, and there is something called open closed map from Hochschild homology of this guy to ordinal homology of x1, the Hochschild homology of x2 of this guy to the homology of x2, and I think the correspondence gives some homomorphism, and probably you need to include some quantum effect, and the conjecture is that this diagram commutes. And one reason I'm interested in is the following things. There are something genetic criterion like Mohammed Absais. So how big this image is related to whether this category generates, whether this is the generator. So if one can prove this kind of commutativity, probably one can use a lot of Lagrangian correspondence to cook up some generating series. But for that, one need to establish this kind of conjectures, and that's interesting. And I want to say that using the direct analytic approach studied by Botman and Wilhelm, it is likely we can prove it. So the idea is this following. So you have this kind of strange thing. You have this disk, which is divided into 2 parts, and you have this something like a kilt-like things. And you put some marked point in interior, that is the output. Then we narrow this strip, and finally you have this kind of things. And I don't want to say so much more, but if it's strip thinking, or this particular problem works nicely, then it seems very likely we can prove this commutative diagrams. And the reason I cannot prove it yet is I don't know how to work it out using this cobordism approach. There might exist, but so this is something I feel it's better to do in analytic approach. Okay. So now this, let me about generators. So I want to raise some problems. So we consider this category associated to this space of flat connection on the Riemann surface. And then we have some kind of handle body. So you have this genus 3 and you have the genus 1. So you get, so just the genus keep increasing, never decreasing. This gives some Lagrangian submanifold on this R of sigma. It's something similar to this 100-body things. And the explicit conjecture is that, so we can find some finitely many, this kind of 100-body, so that these Lagrangian submanifold split generate the all categories. And probably we can specify finitely many of them. And I think there are work by Ivan Smith in the case of genus 2. And why this is interesting is that if it is generator, then if you have some another Lagrangian 3-manifold Y whose boundaries of this sigma G, then you can glue other side of this finitely many kind of 100-body. Then if you know this Floer homology, then it should imply that this relative Floer homology is recovered. So this infinity category, which just have this finitely many thing as an object, knows enough to do this Lagrangian Floer, to do this Atiyah Floer type thing or Floer homology of 3-manifold with boundary. So I believe we can try to find this finitely many things and try to calculate infinite structures on them. That should be kind of make some complete applications of this Atiyah Floer conjecture. And I just do not have, so I just want to say the final conjecture. So suppose you have this simplex manifold x1 together with Hamiltonian G1 action and x2 together G2 action. We assume that simplex quotient, which can be singular, is isomorphic. Then I expect G1 equivalent around the Floer theory on x1 is equivalent to the G2 equivalent Floer theory on x2. That's a conjecture. And I want to say that, I don't want to say that, but this conjecture may be regarded, can be regarded as a version of Atiyah Floer conjecture, as a finite dimensional analog of Atiyah Floer conjecture, where this space of flat connection is singular. But this is a baby version, finite dimensional version, so it should be easier to prove. But you know, if you know that this simple quotient is smooth, then you can just use this the result I mentioned twice to get this one. But since this simple quotient is singular, we cannot do it. But it seems likely we can do it. But I don't know how to prove it. Okay, thank you very much. I stop here.
Do you have questions?
You have a nice finite dimensional example of the last that last slide, like.
I think I don't know so much, but you maybe have some big thing that's two different way of going down. Then this kind of situation occurs, and in that case, probably one can prove it. And finite dimensional.
Maybe asking the other ways, is the fiber product like this master thing always exist, or
No, I don't believe so. But to have that nice finite dimensional example is not so trivial. But you know, the example I have in mind is that if you have this kind of gauge theory case, space of all flat connection divided by, you have a singular simplex quotient. But then there is some other Lagrangian simplex manifold called something called the extended moduli space. And you take some simplex cut to get a compact simplex manifold. And then its simplex quotient is also the singular guy. So
we cannot somehow combine them into one.
I mean, fiber product, the problem is whether fiber product is smooth or not. It seems not so easy to expect.
So this on last page, what is this? I try to understand better this problem. So you say this when R sigma is singular.
Yes.
And there's a finite dimensional a lot of it of Atiyah Floer's theory. What do you mean, really?
I mean, so in the case of R of sigma, it's singular. There is some known constructions so that you represent R of sigma by some finite dimensional simplex manifold divided by some Hamiltonian G actions. So it means that in a case, singular cases, Atiyah Floer conjecture should be this instant Floer homology is isomorphic to this finite dimensional Lagrangian Floer theory, which is not R of sigma itself, but it's a bit more extended.
Mm-hmm. So also during your talk, you mentioned the sigma gauged linear sigma model.
Yes.
So is that related to this Atiyah Floer things, or I just missed some maybe points?
I don't know how directly Atiyah Floer conjecture is related to gauge sigma model. Yeah. But some techniques are common.
Just some techniques may apply.
Yeah. I think this Gangubo proved that the theorem is the following. You have a three manifold M, which has a product type end. Then you take this M cross R. It's four manifold. And one can study instanton AC equation there, which has a finite energy. Then this guy has some nice behavior at infinity. And this equation seems to be related to gauge sigma model. Is that true? Yeah. So this idea is very much popular, common.
Thank you.
So could you say a little bit more about these three manifolds which give rise to Lagrangians which split generate the Fukaya category of the surface sigma?
I mean, I cannot say so much. So the problem is, so there is something similar to open closed map in gauge theory side. This is Lagrangian theory related to some quantum cohomology element of the space of flat connections. And then they have an open closed map. So probably one can calculate this open closed map to this R of sigma. So that how this 100-body Lagrangians gives an element on this quantum cohomology of R of sigma. And then you can try to calculate, and we didn't do these calculations. But I think this, I think we proved in our papers that this open closed map, I mean, this isomorphism between instanton homology and this Lagrangian Floer theory in an embedded case respects to this action of this something like bulk classes. So we can try to calculate this open closed map, and then try to see if you take sufficiently many elements, it generates this. So then we are done. But the calculation we didn't do yet. So I think Ivan do something like in the genus 2 case. And in genus 2 case, I think he found some relation to some pencils and something, and then they are much more naturally related. But if you go higher, then the modular space gets more difficult. But at least this cohomology of R of sigma is known, like by Atiyah bot. So how it's related to this is a kind one need to attack. But we didn't do it. It's just a kind of problem to understand.
But there's like no guess which three
No,
manifolds?
not yet. Yeah. If we have a guess, maybe we can start working. But yeah, maybe you have to try to calculate genus 3 or something. But I mean, homology is not terribly difficult to study in a raw genus, but it's getting harder and harder very quickly.
Okay, so maybe I ask a question. I think I asked you like a long time before, but on the Atiyah Floer picture, the infinite dimensional problem. If suppose you want to do Atiyah Floer type question, so what's the difference between the rank 2 case SU2 and the higher rank case?
I think it is singularity of R of sigma. So I think if you know how to handle this singularity, I mean that sounds like an equivariant theory. Probably you can do anything. I think people like Kroheimer, Mrowka, and most recently Skaudater and those people kind of study equivariant Lagrangian Floer, equivariant instanton Floer homology by many people. So that side probably is okay. And the symplectic side is this R of sigma is singular. And something that we found is that we have some another extended modular spaces, and you take some symplectic cut. Then we still have some smooth symplectic manifold with this group actions. So the symplectic quotient is something R of sigma. So if we can do these kind of things, then probably we can include all gauge group.
Okay, thank you. So if there's no more questions, let's thank Professor Fukaya again.